Hello and welcome everyone to tonight's webinar on problems worth exploring. I'm glad you found the time to join us this evening, and tonight I'll be joined by Carol Moll. I'm kind of running the show in terms of presenting and hosting, and Carol will be joining me shortly. Let's just see if I can get Carol on board. Just bear with me while I track her down.
Hello.
Carol, are you there?
I'm
yes,
here.
We can hear loud and clear. Very good. Okay, so we won't spend much time going through the information at the start. We've got a lot to get through. Carol's got an absolutely brilliant problem on goats, and I want to give her as much time as possible to do that one. Now, if you want to catch up with us on audio through your phone rather than on your computer, there's a toll-free number which you can dial in on, and then you'll need the meeting number. It asks for a pound key. That just means the hash key on Australian phones. The one looks like a little star, I guess. Well, not the star, it's the crossword. And let's move on to the next one. So Carol's joining us from South Australia. Dare I say she's been teaching since the days of log tables, which is okay because that's what I used when I studied in school, was log tables. But needless to say, she's embraced technology more so than a lot of other people, and it hasn't curtailed her passion for the subject. It's amazing. I've spent many a time, if you're not a nerd, then, or rather, yes, if you're not a nerd, I don't think you'd enjoy the conversations that Carol and I have over dinner, because we like to chat maths, don't we, Carol?
We do. We certainly do.
I think if anyone is not involved in maths and has to sit through our conversations, they would cry. Because we do. We're maths nerds, and that's what we love. And I've been teaching for some years, and obviously also passionate about the use of technology, particularly CAS. So my first challenge for participants tonight, I've called it a cup challenge. I refrained from calling it a drinking challenge because I didn't want to encourage anyone to curtail in such habits. And here's how the problem works. So we'll start with 6 empty glasses, and we roll the dice. We've numbered the glasses 1 through to 6. And we've rolled a 1, so we fill up glass number 1. We roll again. This time we've rolled a 3, so we fill up glass number 3. This problem looks really easy, doesn't it? There's no challenge to this yet. Rolled a 5, that's fine. There's a catch though. I just rolled another 3, which means because it was full, I now have to consume or pour the contents out. So we're okay to go now. We've rolled a 4, and we rolled a 1, so now glass number 1 has been emptied again. So we're not making a lot of progress. The aim, by the way, is to get all 6 glasses full. And of course we just continue rolling our dice, and the glasses keep filling, and it's looking good. But of course I'm not going to show you what happens next. So obviously we've got a 1 in 6 chance now that we could possibly finish the game, or there's another possibility, a 5 in 6 possibility that I end up having to empty one, and I could even regress back to having all empty glasses again. So the problem is, how many glasses would you need to, let's say, pour out or drink before you manage to fill all 6 glasses?
Now everybody should actually stop and write down a number. How many do you think?
Yeah. Or even, they could send them in on the Q&A or the chat section. That's a good idea, Carol. They could send their ideas in on the chat space. It is actually an interesting maths problem in the sense of if everybody puts in what they think is a reasonable estimate, we can average those estimates and get an approximation for what the real answer is. So, in fact, I'm not actually going to give them the answer tonight, Carol. It probably sounds really harsh, but I will give them a heads up on how they could get there, and how they could get there in a couple of different ways. So we'll start by having a look at the, let's say, the traditional approach. And that might be, oh, here we go, somebody sent in a guess of 36. That's not a bad guess. It's not a bad guess at all. I'm not going to say whether it's right or wrong, because that would just spoil it for everyone. So one of the problem-solving tasks, or rather skills, that I suggest students use is to solve an easier problem. So let's consider the problem with just 3 cups. I started with just 1 cup, but that was pretty boring because you basically finished the game in 1 roll. But it might be trivial, but it's worth looking at it as far as a pattern. And 2 cups was actually fairly easy to solve. And you can look for patterns with 2 cups very quickly and easily. But the 3-cup problem is very similar to our 6-cup problem in the sense that we'll see. So if we start with empty, so the number of cups, we start with 3, the first one's empty, so we're guaranteed to fill the first glass. We get a 3 in 3 chance, so we'll get 1 glass full. Now that E1 is not the first glass from left to right, it's just any one. So we just want 1 glass full. That's why we've got a 3 out of 3 chance of getting 1 glass full. And then once we have 1 glass full, we've got a 2 in 3 chance with our 3-sided dice of getting 2 glasses full and a 1 in 3 chance of finishing it off. So we can see, we can just apply some basic probability to that and say, there's our chances of finishing straight up without having to empty any glasses. It's pretty close to 25%. A lot different once you've got 6 glasses, of course. And we could start working at expected values because that's kind of what we're after. How many would we expect to have? So, of course, we don't necessarily finish it straight up like that in just 3 straight rolls. So let's have a look. We could get to 1 glass and have to revert backwards. So that's this one here. So in other words, we got 1 glass full, and then there was a 1 in 3 chance that we rolled the same number again and ended up with 3 empty glasses, and we're back to where we started from. So that's not the only way to malfunction in this problem. We could also malfunction from the second glass, or having 2 glasses full. So we could get 2 glasses full, and when we've got 2 full glasses, there's actually a 2 in 3 chance that we could go back to 1 glass being full, but then continue on and finish up just nicely. Now they're the only 2 cases that would take 5 rolls, and you'll notice I filled in the table to say that you can't finish the game this way in 4 rolls because you take a step back, and when you take that step backwards, then you've got 2 more rolls to fill up or 3 more rolls to fill up, and you've already done 2 or 4, whatever. So the chances of finishing in exactly 4 rolls is 0 in this case, but we could now work out the expected value from 5. What's the chance of finishing in 5? And there was 2 ways to do that, and then we'd sum up those 2 ways to do it, and that's the expression that we get, which is not all that nice. But of course, it could go on from there because it might end up going backwards again. We might get 1 glass full, roll that number again, and end up empty. We could do exactly the same the second time round. These are all possibilities. So clearly this tree diagram could go on forever. So it's not an attractive situation to have. So we could resort to a simulation. So what I did is wrote a little program, and my listing is a little bit clunky here, but if anyone's a genuine programmer, please excuse it, but it's quick and sharp. So we start off by saying that we'll set a list of values, 6 values for our 6-cup problem, and they're all empty, hence the zeros. And then we'll use this S and C to do some counting for us. S is actually going to be the sum of the values in our cup list. So as long as that sum is less than 6, then we need to keep on rolling these dice. And of course, C is going to be our counter. So from a programming perspective, there's nothing really challenging here. Then we just have to make a decision. Oh, sorry, we need to roll the dice. So here we are, we're rolling the dice. It's a number between 1 and 6. And here's our decision statement. So it says, if cup number 1, or whatever number has been rolled, let's suppose the first random number was a 1, it says, if the element in list 1 is 0, then fill it up. In other words, put a 1 next to it. The other option, of course, is it's already full, in which case we empty it. We put it back to 0. If we'd rolled a 3 using our random statement, then that would say if element number 3 in our list is equal to 0, then we fill it up. Otherwise, we empty it. That's the brains of our program right there. That's it. And then we just add all the values up in our list. And if that's less than 6, obviously we're not full yet. And then we'll just display the list of values. That's our entire program. So it's not too bad and quite possible to write. And I know in Australia there's a lot of regions now where they're requiring students to do some programming. So our participant that guessed 36 would probably look at that number of 576 and go, ouch. But let's run it again. So there's my little program on the right-hand side, and it's going to kind of look like a binary computer program here. But there it goes, it's simulating. Now I had to put a wait command in this just to make it slow down, otherwise the numbers churn past too fast and you couldn't see anything. So what we're seeing now is it gradually filling. Oh, we saw 5 ones in there, but it didn't fill up. And what we're seeing is any 1 means that that cup is full from left to right, and a 0 obviously means it's empty. And we can see it's toggling between, it's probably hovering around about 3 or 4. Oh, there it goes, 220. I dare say I'll do one more roll on that and let it go. So 220, we had a 500 and something. Let's see what this one ends up to be. And some people would probably be just about ready to review their thoughts on how many rolls it might take. You can see the probability tree diagram in this case is potentially going to be quite big because our simulation at the moment, oh, there's a short, oh,
that was, someone was right.
Good. Someone said it was 36. Maybe we should stop right there. I won't do any more simulations on this one because I think people have got the general idea. So we'd probably want to try more simulations than that. So what I did is I added to my program and said, well, let's have a look and we'll request a number of trials. But this time it's not actually going to display the dice rolls. Instead, it's just going to tell us how many turns that it took to actually solve the problem. And that's going to go past pretty quick. So I call this cup game number 2. Cup game number 2 says, well, how many trials would you like to do? I'm going to do 100. And you'll see it races past pretty fast and it's done. So it's actually played the game 100 times, and you can see some of the numbers there. They zoomed past pretty fast, so let's have a look. It dropped them in a list for us, and here they are here. So the first game took 60 goes, 46, 12, 32, 8. So we can solve them. That's pretty short, isn't it, 8?
Amazing.
Not much of a game then, was it? So you can see it's bouncing around. There's some small numbers. But let's say it's a very large standard deviation on this. So it would probably be worthwhile estimating the mean. Now, we can estimate the mean. So let me just go back up here. So we'll bring some stats into this problem. And let's do a confidence interval. Oops, jumped out way too fast. Let me do it one bit at a time. Oops, there we go. So we'll do a confidence interval, T interval. Now, depending on what region you're from as to whether or not you're using T, I think most regions are probably using Z where we have a known mean, but in this case we don't. So the list of values I'm using is in this TC. Each value occurs once, and we'll use a confidence interval of 95%. So we get an average of 83 rolls. And we're 95% sure that that population mean lies somewhere between 67 and 100. Around about the 83 is where we're thinking. Let me just go back here then and run the program again. And one of the things that we try and get across to students is that the more samples you do, our standard error being, what is it, Carol, SO with a square root of n or something, isn't it?
That's right. Mm.
So let's run 500 trials, n being a lot bigger here this time. We should see a smaller standard error. So it's zooming through 500 trials of our game, and it's done. And now let's have a look. The calculator's automatically redone, and look at that, our mean is very close to what it was before. It's automatically done our t-interval again, and we can see that our upper and lower regions are now a lot tighter because we increased n. S over root n gives us a much smaller standard error. So now we're quite confident, well 95% confident still, but a lot more predictable. We're saying that that mean should be somewhere between 77 and let's say 90. So now we've got a rough estimate for our answer. So we're exploring the problem a little bit further, and that's our program there. So we did hundreds of simulations. Now, for those people that want to determine a solution, perhaps algebraically. Now, I'm not going to solve the algebraic solution here because I want to pass across to Carol in 2 minutes' time to give her enough time to get through the goat problem. So let's suppose we consider the problem, and this is a different way to look at the tree diagram. Let's imagine we're starting with, it's kind of like a glass half full solution. In other words, we're looking as though we're really close to the answer. So we saw in that simulation that sometimes we get 5 glasses full. So this is the chances that we're at 5 glasses. Where can we go from there? Well, there's a 1 in 6 chance that it will take one more move. Or there's a 5 in 6 chance it will end up with 4 glasses full. And to get to that place, we'll have taken that one extra move. And that's why I've got 5, 6 times 1 plus the chances of finishing the problem from a 4 glass full. Now, they're the only 2 situations we can have from 5 glasses. Either we end up finishing the game or we go back to 4 glasses full. And if I knew what the solution was for finishing the game from 4 glasses, I'd have my answer. Well, from 5 glasses anyway. We can supply the same logic as if we had 4 glasses full. So there's only 2 ways we can go. We can either end up with 5 glasses or 3 glasses. And in each case, it's one more move to get to those spots. And there's a 2 in 6 chance we'll go to 5 glasses, and a 4 in 6 chance we'll regress going back to 3. I think most of you will start to pick up the pattern here. So what's the chances of finishing from 3 glasses full? Well, we've got a 50-50 chance we'll go to 4 glasses, a 50-50 chance going back to 2 glasses. And if we had 2 glasses full, we've got a pretty good chance of getting up to 3, slightly smaller chance of regressing back to 1. And I think most people realize now that we've got quite a few equations. In fact, we've just accumulated 5 equations with 5 unknowns. And our set of equations looks something horrible like that. But if we go through E5, E4, E3, E2, E1, and E0 are our unknowns, and there's our equations, and from there we can do simultaneous equations, and the value that we're after is the expected value starting from empty, so we're actually after the E0 one. That's the one that we ultimately want to resolve. So to solve E0, we need to figure out what E1 is, and to solve E1 we do E2 and E0. It sounds circular, but it's okay. Just treat it as an algebraic problem. You've got enough equations and you can solve it. But I'm not going to solve that here because I'm out of time and I want to pass across to Carol. So I'll stop sharing my screen.
Hang on while I get mine set up.
Yeah.
Here we go. I'm ready to roll.
So I'll change across to you, Carol, and Control-Alt-D, use your shortcut to share your screen. And just while Carol's getting her screen ready, if you have any questions, please use the question and answer or the chat space to send information to us, and we can try and answer your questions.
Now we should be right.
The gobbling goat problem. I'm glad you didn't put a photograph of me in there, Carol. I know that must have been tempting.
Very tempting.
You've had me over for dinner before. I probably am a gobbling goat.
Ah, dear. Okay, this is a problem that I came across only this year. I'd never seen it before this year, and I shared it with my university classes who are pre-service students doing final year BEds or graduate diplomas. And I thought it was a good opportunity to show them what I call scaffolding a problem. And really it's about saying, how do we get students to try to work on a problem like this one and really be able to work out what the heck they do. And there are various ways to do that, which I'll try and show you. So here we have a grassy field in the shape of a circle with a radius of 100 metres, and it's enclosed by a circular fence, so we don't count the grass outside that. A goat is attached by a rope to a hook at a fixed point on the fence. So the question is, if the farmer wants to stop the goat getting too fat, he wants to ensure it can only reach half the grass in the field. Not a particularly realistic question, but that never stopped me in the past. How long should the rope be? So that's the question. The radius is 100 metres. How long should the rope be, so that the goat gets to eat only a half of the grass that's in that circle? Now, would you please write down your estimate of what the length should be? It's very important, I believe, that you scaffold problems like this, but also include time for students to have a bit of a guess. And I think sometimes you also need to understand that kids might be introduced to problems like this quite a few years earlier, where they don't have all the mathematics that's required. You put it in a slightly different context. And I call that creating hooks in their head to build knowledge on later on. So what Peter talked about, making the problem a bit simpler before, I agree with that totally. The other point I should add too, by the way, is that because I'm from South Australia, we're not up with CAS yet. There's no plans in the foreseeable future to go to CAS, which is interesting. So TI-84 is the best we can use, and of course the lovely TI-84CE and its emulator is what I'll be using at the moment. So you've all written down your estimate. I hope you realised it needed to be at least 100 metres because he would only reach the centre if it was 100, so somewhere between 100 and 200 metres of rope. If you said 200, of course, he could eat the whole field, so that wouldn't work. Now, this is an example of a problem which is pretty open, I think, and quite difficult to get started on, depending on the goats, what goats you're teaching, at least I'm talking about here. So it depends on how good your students are, how far you can get with this one. The first thing you must do is draw a reasonable picture of the situation, and then think about what else can you actually work out once you've got a reasonable picture. And where do we go from here? And what maths content do we need to actually know? So at this stage you should have a circle already drawn, the goat attached at perhaps the right hand side, furthest extremity, and a bit of an arc into that circle, which is the area that the goat can actually graze on, and it is to be only a half. So the best way to deal with this is perhaps to change the problem a little and see if that helps with the maths to be used, because some students won't have a clue how to deal with arcs of circles and so on. So this is a bit of scaffolding, as I would call it. Have a think about what other options there would be for tethering the goat. And so, for example, what if the goat was tethered to a pole in the centre of the field? So that's an interesting problem as well, because many students would say, oh, that one's easy, we'll just make the rope 50 metres long and let him be right in the centre and he will eat half. Well, of course, we know that that won't be the case, but I think students should certainly explore that idea. So suppose the rope is 50 metres long. Calculate the area available to the goat if tethered at the edge as before. If this is likely to be more than or less than, is this likely to be more than or less than half the area? Well, of course, I think we've realised that the rope has to be at least 100 metres long since the radius was 100, but we could work with the 50 metres and just do some calculation and then suggest another value for the rope length and try that, etc. So I am a great believer in not having kids lunge straight into algebraic stuff, but actually do it numerically, and they start to work out what mathematics is actually required. So you could actually give all the members of your class a different length for the rope and get them all to do some calculations with a specific length of rope, and you'll eventually get there, of course. And sometimes you even need to simplify further by changing the shape of the field. So, for example, in a square field with sides of 100 metre, first of all, what possible options does the farmer have for tethering the goat? He could tie it to a corner, Now that introduces a bit of arc work, perhaps, or perhaps just a quarter of a circle. If you was at the middle of one side, you've got an arc of a sector at least of a circle and a couple of little triangles, so that starts to get a little bit harder. Or of course it could be in the centre of the field. And again, I'd try each of these options with a given length, class members using different range of lengths and so on. So now we're probably ready to have a go at the original problem. I hope you like my little goats looking in from the side. What mathematical content have you used in the exploration so far? I believe it's always important to try and say, well, okay, we've had a go at doing this exercise with some numbers. What mathematics have we actually used? And you also need to be thinking about which year levels you might use this question for. And as I said, it might be that parts of the question can be used with younger students, and then the problem can be reintroduced in a later year with more difficult content. So, to solve this problem, we need to use areas of sectors and segments and some right-angled triangle trig. You can have a look at this later if you want to, because I believe these will be available for download. But what you can see is there's a dark green area, which is going to be the area that the goat can graze, and it involves the area of a sector with an angle of 2x at the point B. But then, of course, there are a couple of little segments along the lines AB and BC, the chords AB and BC. So we've got quite a bit of hard work to do there to actually do this calculation. So the dark green shaded area can be divided into 3 bits. And so the area turns out to be the area of the blue sector with a length of rope which I've called R, and the angle being 2x, plus a couple of little yellow bits which are segments on chord lengths of length R as well. Now, there are various ways to find this total area to be grazed, and I've put this together in an additional document called the Gobbling goat problems or ideas or something or other, but that'll be available for download. So the problem we have in this question is that there are 2 unknowns, the angle x and the rope length, and cos x, you'll be able to work out, turns out to be r divided by 200, and so x is cos to the minus 1 of r over 200. Now you can actually find the area in terms of r, and the hideous formula is that one at the top, area equals r squared cos to the minus 1, blah, blah, blah. So what you'll see there is you've got, provided the angles in radian measure, of course, which I didn't mention at the start, but it would need to be in radian measure. R squared cos theta, R squared theta, possibly should have a half in front of that, I'm not sure now. But we've got an area of a sector. No, it's actually 1/2 of that whole sector. That's why it hasn't got the half in front, because I'm doing it through the half of it. That's right. Plus the area for a segment, which is that one. So the task is to solve for r when this is equal to half the area of the field, which is a half pi times 100 squared. And clearly you can't solve that other than by approximations or graphically. So since this expression is fairly horrendous, I've entered them into my CE emulator and saved them as a GDB. Now, I had forgotten this myself, I haven't used it for a while, but for those of you who aren't familiar with this, a GDB means saved as a graphical database. This saves time and errors later on. So on my calculator, which you can see at the side, I'm going to press second, program, and scroll across to store, and you'll see that I can store a GDB or recall a GDB. Now, of course, I need to go down to number 4 or press number 4 and tell it that I've stored it as GDB1. Actually, before I do that, just so that you know, I'm not cheating here, there's nothing in my y equals at this stage. So I'll just go back to here, scroll up, and no, it won't let me grab that anymore. I'll just clear that. Back to second program, store, number 4, graphical database number 1, enter. And now the good thing is these totally horrible equations have now been entered straight into y1 and y2. And all I need to do is graph. So I'm going to press graph. That's the fixed area. this is the horrible formula. It takes a long time to work this out because it is taking various values of x, having to find cos to the -1, etc., etc. Now I need to try and find out where they intersect. So we're going to do second calculate, intersect number 5, enter, enter, and away we go. Okay, so the intersection is at x equals 115. Peter, are you still there?
Yeah, still here.
Okay, something's going wrong with our phone out in another room. But, okay, so I've gone through this and I've shown you that. So we now have found that the length of the rope for the goat needs to be around 115 metres. So the big question is, of course, how was your guess? Hopefully you will have got somewhere near that, but it's very interesting to see that you can actually do it using the intersection of the two curves. Another way to do it, of course, which is in the notes that I've put out there, is actually just in a spreadsheet type table, which is also a bit horrendous, but it's not hard to set it up. So that's the first bit of the gobbling goat question. Now, Peter, first of all, does anyone have any questions about that?
I haven't seen any questions coming in. But here's an interesting one for you, Carol, in terms of what I was doing recently, and I've just added to my little document. I took note of your first one. That was where you said, let's go for an easy problem, and on the calculator I drew a circle of radius 50 metres. It was 50 metres, wasn't it, the original one? And then did another circle inside it. And I think it's really nice to have students see that their initial instinct, I guess, is wrong. Otherwise, they're reluctant to try it. That is, oh, well, I'll just do a radius of half the other one, and therefore I'll get half the area. Because it's a common problem. We see it in Year 9 with squares, and making it a circle probably makes it even harder for them.
Yep.
Totally.
Do you want to show that on your screen?
Yeah, I can share that. Just let me...
Not sure mine then, but go on.
There we go. Let me just drag that back. Share screen.
Yeah.
So here's the one, and you can see what I've done is I've just made one circle on the outside and another one on the inside, and I dragged it until such time as I got a ratio of a half. So I've got the area of the smaller one divided by the area of the large one. It's measuring them both for me. It's telling me the radius. I did mine 100 metres rather than 50, but that's okay. I'm still getting the same idea. So if I do one with half the radius, I can see I've only got a quarter of the area, which is what we'd expect. Well, as math teachers, that's what we'd expect. And of course, I can make it bigger, and I want to get that ratio equal to a half. And it's kind of like the pizza problem, isn't it? You know, you have a look in the pizza shop and you say, oh, I'm paying twice as much, but my pizza doesn't have twice the diameter. Well, you'd get 4 times as much if you had that.
Yeah.
But I mean, this is
one of the beauties of Inspire compared with the TI-84. I can't draw diagrams like that quickly and make them interactive. I mean, you can do it on Cabri, but it's pretty clunky. So yeah, I would have to do that sort of thing by hand, yeah.
Now, it's interesting because the second problem where you tether the goat to the perimeter of the circle somewhere, there is no nice shape that allows us to directly measure the area that's enclosed between the two. So I kind of cheated, and what I did was just did a multi-sided polygon, which is kind of all right because we're just approximating it to begin with to get a feeling or a sense of the problem. Again, if we're talking problem-solving strategies, one of them is just start throwing some numbers at it. Well, what I'm doing is just throwing some diagrams at it to get a sense of where the problem's at. And you can see I can change the size of the circle. The good thing is that I can see very quickly, if nothing else, just from the diagram, but also from the calculations here, that I'm not getting half the area. I mean, I can see it's obvious. I'm not getting half the area enclosed between the two circles, so the goat wouldn't get to chew up half the paddock. but I can get a rough idea if it's a 100-metre paddock, 100-metre diameter, 100-metre radius paddock. I can see that the other circle would need a radius of 122 metres, so I can get a rough idea. And I think that's similar sorts of numbers to what you were getting.
Well, 115 is the right answer, but of course your calculation's leaving out all those little bits around the edges, etc.
That's exactly right.
That's great. No, it's great the way you can do it on Inspire.
Yeah.
Okay.
So I'm sending that back to you now.
Okay. Share my screen, see if this comes up
Questions
again.
coming in. Mr. Lennon says, I've got a goat, which I can tether.
Who said?
Yes, Mr. Lennon is sending us some curveballs, Carol. Consideration also needs to be given as to whether or not the goat will get tangled up. Thank you, Brian. All right, we can see your screen again.
Go and get yourself a cup of tea, will you? Go and get yourself a cup of tea, Brian, and worry about your own goat. I'll worry about mine. Mine is not getting tangled up. So, extending the idea further, this is where the problem becomes quite a lot nicer, and this is the part I really enjoy doing on the calculator, even though it's the clunky TI-84 in lots of your eyes. So this time we've got another goat tethered at a single point on the side of a circular water tank of radius 1 metre, and the rope goes exactly half the way around the circumference of the tank. So what area of grass is available to the goat? And a full solution to this one uses parametric equations, circle geometry, and a bit of calculus. So this is a lovely, lovely problem. So suppose the goat is tethered like this, where the rope is exactly half the circumference of the tank, which has a radius of 1 metre. So the first question you need to ask, of course, the obvious one, if the radius of the water tank is 1 metre, find the length of the goat's rope. Now, you can all write down, of course, that that is pi. So, the next problem we have is that clearly the goat can eat a semicircle out from the bottom of the circle there at the bottom of that central radius, but as the goat moves upwards around the circle, the rope this time does get to wrap around the tank. So the length of rope beyond the tank decreases, and my little diagram shows a bit of that. Now, I would like you all to stop for a couple of seconds and actually draw the area that you think this goat will be able to graze. It's a bit surprising when you actually work it out. So I thought this question was probably related to, the point on a rolling circle called cardioid or something like that, if I remember rightly. That's what I thought it was going to be related to, but it actually isn't. So if you've got some sort of rough diagram, let's push on. So this is the important bit of it now. For a small increase in the angle, let's say pi over 100, the angle theta is going to move from 0 to 100 to get the goat right back up to the top. Now, I haven't drawn you any diagram of what the goat can graze, but I'm just going to move you through the mathematics that's there. So let's suppose that that angle pi that the goat will move, the rope will move to as it goes around to wrap right around to the top of the tank. Suppose I divide it up into 100 little bits, each being pi over 100. So for every little angle theta that the goat moves through, the rope left that he can eat out from is actually pi minus theta long, but a tiny little move around the circle creates another line that's slightly less than pi minus theta, but it's actually pretty close to pi minus theta, and it creates a little sector. So what I'm going to try to do is add up all these little tiny sector areas that actually have length pi minus theta. And so the area of this sector is approximately a half L squared times pi over 100 if I have 100 small divisions. So draw a diagram showing the area the goat can graze. Well, you've got that. This does take some thinking conceptually, and if you test a point halfway around the circle, for example, this is really quite surprising. When you're halfway around the circle, the tangent to the circle will go straight upwards vertically. But the length of the tangent is going to be pi minus pi over 2, which is still pi over 2, or approximately 1.57. So what does this actually mean on the diagram? It actually means that the goat will be somewhere up here, distinctly above the top of the circle. So there's something interesting going on in the shape. So we've done that one. Find the area that the goat can graze. Again, now the area is going to be the sum of all those little bits and pieces. So first, of course, the goat can eat half the circle of radius pi below the bottom of the silo, and as it moves around, the tangent to the circle gets shorter and shorter and shorter as he moves up towards the top of the circle. Now, an interesting mathematical exercise, which I haven't written out for you, but it's worth getting your students to try to do, is find the parametric equations to represent the end of the rope as the goat moves. And I was quite pleased to be able to work this out, and this is what they turned out to be. If the endpoint is P, then the point XY has X equals sine theta plus pi minus theta cos theta, and Y equals that. So back to the CE and change into parametric mode. So I'm just going back over to here now. So we're going to change the mode, and this time I actually have the equations already in there. And you'll notice that I've actually got a couple of others in there as well. The red ones are going to be the circle, which is the tank, and the black ones you'll be able to work out what they are in just a tick. So I'm going to graph those. So we'll see what happens on the graph. Well, nothing much, but that's because of the axis. So I'm going to zoom trig. Oh, I seem to have an interesting set of circles and part circles there. So I'm now going to say zoom 5 to just square it up a little bit so my circle looks a little bit better. So the red circle is the tank, and the part below the blue line and down to the bottom black circle, of course, is what the goat can actually graze, which is really quite surprising when you look at that, I think. Well, I find it surprising anyway. And the idea is that the upper part of above the blue part there is area that the goat just cannot reach, because when he's right up at the top of the red circle, he can't reach any further. Now, we're not worrying about the length of the goat's nose or whether he's got his rope in a tangle or anything, but it's a beautiful little problem, I believe. So, what are we going to do from here? It would be nice, Peter, we said that we really didn't like the fact that the the black circle went all the way around, so I've actually stored that, I hope, in GDB3. Let me just check.
And just like Carol's doing that, I did play the other day with drawing a geometric diagram of the same thing, but I do like the fact that obviously we can produce equations for it, because as we saw before, the geometry produces a nice solution, but then we're getting the CAS to do all the work for us, whereas this is using some of the equations, which I think is much better.
So there it is. For the black part is where the goat can graze straight out on the full length of pi, but the blue and red contain the bits he can reach, and those two circles, the bottom part of half circle is the black one. Sorry, I'm a bit tangled up there. So it's pi lots of cos of half t, and minus pi lots of sine of half t is what actually gets it there very nicely for us. So that's a neat little way of looking at the area that the goat can graze. Now, of course, how do we calculate it? So what I've actually done next is I've used lists to divide the pi into a number of small equal increments. So to have 100 divisions, we need list 1 with 1 to 100. So I've already got those in the list. So list 1 has got 1 to 100, and you'll notice that list 2 and 3 are doing things. It's a little bit slow at the moment, but I've put 100 divisions in there. So let's keep going. I was interested to see that while I'm in parametric mode, as soon as I try to go into sequence mode, the calculator expresses the t as the variable very neatly and so forth. So I've stored my 100 in there. Now, the length of the tangent at the nth point around the edge of the circle will be pi minus whatever number I'm up to in the list 1 part 20 or something like that, that many multiples of pi over 100. And so I've actually added that to my second list, pi minus L1 multiplied by n over 100. And so I get all these little lengths of the tangent being calculated. Now notice also that I've got the quotation marks around that formula, because later on, if you wanted to, you can go back and change that 100 to 500 or 999 or however many you want. But of course you would then need to increase list 1 down to 999 or whatever it was you're going to divide it up. And I've put a bit more information in that Gobbling Goats Ideas Word document to show you how to go about doing that. So at this stage it is worth checking that halfway, i.e. at pi on 2, the length of the rope is also pi on 2. And so I can scroll down that list, or I can go back to the home page and I can say, let's have a look at list 2, calculated at 50. And yes, it is 1.57, so that's a relief. My formula works. And also, of course, I could do list 2 at 100, and hopefully when I have 100 little bits of my increment, he has nowhere to go. Correct. Okay, so that's good. So I'll put those in there to remind you to do the L2 of 50 and L2 of 100, so that's all right. Now, this is the interesting bit. I actually then have to say, well, I need to find the area of each sector. So they're approximately half r squared theta, and each little sector has an angle of pi on 100 in it. So if I go back to my list, these guys are actually in list 3, which is coming up. And so list 3 is a half of L2 squared, the length of the tangents, multiplied by the angle in radian measure, of course. And then I need to add up the list, second quit, and then do sum of list 3. I won't bother to go through that because we'll run out of time. So it's quite a neat little problem, that one, to actually use the list as a very powerful way of actually working out your little areas, I think. And another question for your better students, which occurred to me but which I haven't actually done yet, I wondered whether that area above the blue lines where the goat can reach to the black circle is exactly the same area as the red circle, the bit that the goat is actually denied in the middle. And that's an interesting little task in itself, but I haven't done that in the solution that I've given you. And the other thing that was interesting for me is I stored the lists as a group called goat, which is second plus and then 8, so I'll just show you that, second plus. You can actually go to number 8 and you can create a group, and so I've stored it as a group. But unfortunately I discovered that when I stored it as a group, which meant all the lists that I had stored, the formulae were lost, so I won't bother to retrieve that because the formulae are actually gone, which is a pity. Now, to find the area algebraically, just to finish off quickly, Peter, and then you can go back to finishing yours, consider the length of the tangent as a function of theta, which is pi minus theta. And so the area is composed of a number of small sectors with area a half pi minus theta squared d theta, where d theta is the change in the angle. And adding all these areas together becomes an integration problem. So it's really interesting that that's 5.1677, and when I use 999 little divisions in there, I actually got an area of 5.16 with the sum of 999 divisions, which is really incredibly close. And so you get the total area that's grazed by the goat being 25.84 units. So there's quite a lot of mathematics in that, which I find really beautiful and really enjoyed doing. And I think the main thing is that it's a problem that lends itself to the 84 quite neatly, but I'm sure it would be far better done on an Inspire. So Rodney Anderson, when you've finished putting it together on Inspire for me, you can send it to me, and I'd love to have a look, because I think it will be far more interactive on Inspire. But nonetheless, a beautiful problem, and one that I enjoyed presenting to you. So I shall just hand back to you, I think, Peter. I actually said at the end of this that there's a PowerPoint file and a Word document available as downloads, which I presume Peter has set up. And if you want any more information or want to talk to me or send me something, I'd be very glad to get an email from you. So thank you.
Thank you, Carol. I like that problem because you have different entry levels as well. I mean, you looked at, say, the circle being inside the circle, as in having the goat tethered at the middle of the paddock, and that really starts back in year 8 when they're looking at areas of circles.
Yeah.
And then there's several spots where they wouldn't have to have it pegged in the middle. They could have it pegged anywhere close to the middle. And then it really goes out to specialist math when you're looking at parametric equations and calculus, which is really good.
Yeah.
So what I've got on my screen at the moment, I was going to do a different problem, but Carol and I were talking about this one before. And here's the problem as it's presented in the general arena, and that is that it's called Pebbling the Chessboard. And believe it or not, it actually lends itself to sequences and series. So the problem that we have is we've got 3 disks enclosed in this little grey area at the bottom of the screen. And the simple task is you need to get them out. Now, the trick in getting them out is that when you move them, they split into 2 pieces. So the task that I've written up for students to explore, which you'll be able to download from the website as soon as I've loaded in, looks a little bit like this. I made the area a little bit bigger so that the students would jump to a conclusion a little bit quicker. And let's have a look how it works. So it involves, again, still the same problem, trying to get the disks out of the shaded area. And disks can only move forward, they can't move backward. They move one space at a time. And each time it's moved, then they split into 2, one going forward and one going off to the right. And there's one last rule, and that is you cannot place one disk on top of another, and they can't share the same space. So let's have a look what a move looks like, and there you see I moved one of the disks and it's split into 2, one going up and the other one going off to the right. And then we do the same again. So it's moved up and to the right, and then again up and to the right, and we're getting there. We've done 4 moves. We've still got 3 disks in there, but you'll see after 6 moves, we've already cleared out 1 disk. So even with this problem, where I've made the grey area a little bit bigger for the disks to get out of, we've managed to get 1 disk out in just 6 moves. But we need to make some room to clear out the next disk. And so that problem continues. Now, looking at the time, we're very close to time. So I'm just going to fast forward to part of the solution process. You'll see on the screen there now that the board starts to get crowded, and I still haven't got any more disks out. So let's have a look what that solution looks like. Now, I'm not going to go through the complete solution, just to show you some ideas of some patterns and how you might want to tackle that solution. Let's just jump into here. And in our solution, let's say that each disk, or each of the original disks, is assigned a point value. Now, the reason for assigning them a 1, a half, and a half, you'll see in just a moment. So when a disk is moved and splits into 2, so does its value. So if I move that half disk out, it turns into 2 disks with a quarter on each one. So then if I move one of the discs with a quarter on it, they become 1/8. And then as I move further, 1/16. Now if you've been following me along here, because it splits into fractions whose sum are the same as the original, that would mean that the total sum of all the discs present in the problem at the moment is still equal to 2, the 1 plus the 2 halves. And really our problem is to get all the discs to the outside. Now since the sum is invariant, that is the sum of all the discs is not changing, then we can now reword the problem and say, I need the sum of all the discs outside the grey area to equal 2. Because originally we had all the discs having a sum of 2 inside the grey. I need all the discs outside, and that means the total sum of all the discs, however they be arranged, that sum is still going to equal 2. So the sum of all of the values outside will be 2. And if you have a look at what's on the screen at the moment, we've already got some signs of, let's say, I'm going to call it a geometric sequence. It looks something like that, and you need to start doing some sums. Now it looks a little bit ugly there, but I can assure you once you start breaking it down, you'll see more patterns. It's a lovely problem for students to explore the sum of a sequence. You can have a start and end point, or you can say, let's make the problem easier and extend the board on forever. That sounds as though it would make it really difficult, but it doesn't. Then you can just use the sum of an infinite series. And that formula is quite easy, and I'm not going to show it here because we're about out of time, and it's in, I think for most schools, it would be in their Year 11 syllabus to do the sum of an infinite series. So that's all we've got on that one. That problem will be up on our website shortly, and certainly all the participants, they get the sneak preview, they get the early version of it before everyone else gets to see it. So we're about out of time, and just before we close up shop, just wanting people to be aware that if you live in Victoria, there's a couple of workshops, 3 workshops that you can register for, one in Ringwood, Warrnambool and Mount Waverley in June. That's the school holidays, so you don't have to get your school's permission to attend. If you're somewhat north of the border up near Cairns, then there's the QAMT conference, and if you're quick, you'll be able to register for an extra event the day before the QAMT conference. And on a final one, just to keep abreast of all of these things that are going on, sign up to the e-newsletter so that you will hear about when these events are occurring. So we're out of time. I'd like to thank Carol for presenting our goat problem, and if you enjoyed the webinar, please let us know, because Carol and I would like to provide more of these problem-solving challenges for our webinar series. Just like we have some on IB, we'd like to do some for problem-solving. Thanks very much, Carol.
Thanks, Peter. I've enjoyed it. Thank you.
And thanks everyone for joining us. And that's all for tonight.